Okay, my name is Jonathan. I'm from the University of Fulda in Germany, and today I'd like to present MIPos, a system towards mobile image positioning in mixed reality web applications based on mobile sensors. So the basic idea behind MIPos is that you have a virtual environment of a real place, so a real existent place. And within this virtual environment of this real place, you can use inertial sensors of mobile devices to recover the user's position inside this virtual environment. You use this position to map images from the device's camera to its corresponding position in the virtual scene. The overall motivation of this idea is that mixed and augmented reality always needs to combine somehow a combination of real-world content with virtual worlds, or vice versa. And mobile devices and their sensors should offer various new possibilities in order to achieve this. And also the standards of WebGL and WebRTC make mobile mixed and augmented reality web applications far better feasible than it was before. So, and the more specific motivation was based on a project which combined classical planning data with unordered photo collections in order to supervise construction projects. For that project, we started with some other approaches to arrange images in virtual scenes. First of all, we used bundle adjustment, which was able to arrange real-world images within cut scenes based on detecting scale invariant feature transforms, so-called SIF features. That way we were able to place unordered photo collections within a virtual scene. This approach was very precise but also slow, and the mapping between the image collection and the virtual scene was quite an intense process. So and furthermore, it was not really real-time capable. So we came up with a much simpler solution, which was the manual positioning of images within the web scene. So basically the user could take images within the web application and position those images via an overview of the scene by drawing the view area and the direction of the image on that overview. So then we searched for a better approach which combined the real-time aspect with the preciseness of the bundle adjustment, and we took a look at the current state of the art in this area. So first, one paper which inspired us was in the area of mobile mixed and augmented reality, a paper from Langertz who showed that mobile web applications can interact and create content for mobile and mixed and augmented reality applications. And he also used sensors and the built-in cameras of the mobile device to make his application location aware and to place the point of interest in maps of images. And in the area of mobile indoor positioning, Gusenbauer was another paper which exploited heavily the characteristics of a large set of human movements in order to achieve self-contained indoor positioning systems on mobile device. And he also created or stated that it is feasible to to use step patterns, various step patterns to detect movement based on inertial sensors. So that inspired us for the MIPos concept, which I'd like to highlight the several aspects of that concept here in this presentation. So the first step MIPos does is to get the initial location of the user and the virtual scene on Earth, which is done by the geolocation API. Accessible virtual scenes are stored in a database and defined with several metadata, which is used to identify if a user is close to a virtual scene. So therefore, the metadata for a virtual scene should define a reference geolocation point for the geolocation point, which provides a longitude and latitude value, and along with a rotation angle against the North Pole, so that we can recover the initial position of the user, and which we assume is the entry point of the virtual scene. So the next thing MIPos does is, after gaining the initial position, we embed the video stream as a semi-transparent overlay into the Web 3D scene. Therefore, in order to do that in the right way, we need to extract either EXIF data from the taken images, or we also created a self-hosted camera database, which provides camera-specific field of view parameters for different devices like tablets, smartphones, and other webcams, so that we can adjust the virtual camera in the virtual scene with the real-world camera, so that the mapping between those both is almost accurate. So further, we also adapted the resolution of the embedded video stream to the device capabilities. So we reduced the resolution for smartphones, tablets, and desktop computers. In another step, we detect the orientation of the device in space by using the internal gyroscope data, which is accessible via the device orientation API, which defines the orientation angles for each axis as a set of intrinsic tape prime angles called alpha, beta, and gamma, where alpha defines the amount of rotation around the z-axis and correlates to the compass heating. Beta defines the amount of rotation around the x-axis, and gamma defines the amount of rotation around the y-axis. Since sensor data coming from the gyroscope or accelerometer is mostly noisy and not straightforward usable, there has to be a pre-processing step in order to retrieve meaningful data. So since when it comes to orientation, then the gyroscope has the tendency to drift, which means if you return oriented or rotated a device and bring it back to its initial position, the rays won't return back to zero. So in order to remove this drift from the gyroscope data, we use a complementary filter, which uses the data from the gyroscope in the beginning, because this data is invariant to external forces, but on the long term we also include the data from the accelerometer, as this data is not affected by drift. So basically on this diagram you can see the red line as the output of the complementary filter, and have no idea. The green one is the original orientation data, which we get from the sensor, and with the formula above the diagram, you can see the amount of data we take from the gyroscope and only a little bit from the accelerometer data to wipe out the drift. And on the next step, we also need to react to the way a device is held by a user in order to ensure that the rotation values we receive are valid for each axis and we return reliable data. So in order to do so, the W3C specifies the screen orientation states which we can use to apply the scheme underneath to correct the values we receive from the gyroscope and use that as filter to get orientation values which are insensitive to screen orientation. So next we want to detect the movement of the mobile device based on mobile sensors, especially based on the accelerometer data. And as the accelerometer data itself is really hard to use for detecting movement, we choose to use a step recognition pattern, as steps follow a quite detectable and recoverable pattern, which within the sensor values over time. And so, based on the schema of the sensor values for the x-axis, you can quite easily see that the step is more or less always identifiable by a certain different changes in the direction of the accelerometer values. So therefore, in order to get meaningful data, we used two thresholds: one for a minimum acceleration in order to take this acceleration change into account, and also a threshold for minimum acceleration direction change to be used to reliably detect an acceleration change. And with those values we get from those acceleration changes, we can use a direction model and encode those changes in this direction model and get a list of associated numbers with those direction changes, and we get a column of numbers for all direction changes, and we have several stored step patterns with which we can match those values, after that we can quite surely say if it was a step or not. But there's also still another problem, that by detecting the movement direction of the device, as the user can still move in another direction than the device is pointing at. So, for example, if the user walks sidewards. So, therefore, we needed to separate, to calculate a separate movement direction angle, which is done by also applying by using the acceleration values and generating a displacement vector between 2 points represented by the acceleration values at a given time and for the axis of the current movement plane. After all those pre-processing and post-processing steps in MIPos, we finally get a position within the virtual scene, which we can use to place images within our test application. So in this image, or in this line of images, you can see in the first row images showing the 3D scene from above. So basically the overview of the 3D scene with the user's position and orientation, so marked by the red line in that. And in the second row shows the third-person view of the user, where in column 8 the camera video stream is embedded at the current user position, where you can still see the virtual scene in the background and the semi-transparent overlay of the video from the device's camera in the foreground. And in column B, the user already walked to the desired position in the scene, and in column C, he already captured the image on that position. It is already embedded and placed in the scene, and the user in the last column also walked away from that position and look at the final result from a different view. So, what can MIPos be used for? First, as we use it for construction supervision, for example, where images can be acquired via MIPos and can then be used to find difference between the current state and the planned state pictured in the CAD planning data, for example. And also another use case would be the tracking of changes on a real-world object. So, for example, 3D image positioning technique in web applications could be used to make pictures on the right position of a real object, and just those images then can just be used to track changes, for example, of a building or a statue over time. Another use case would be also Web 3D interaction scenarios, where we can just use the acquired sensor motion and orientation data to control Web 3D applications. But before we can do that, we also just need to prove the universal suitability and usability of this approach by applying an extensive user study, which we haven't done yet. And also we need to develop strategies to deal with the loss of sensor calibration. Yeah. Finally, thanks for your attention.
From what I've seen, you mostly focus on horizontal movements.
Yeah,
what about stairs?
Or not
ladders, because in programs we have lots and lots of ladders. So maybe just let's start with stairs. How would it be to?
Probably not that hard. You just have to find the right patterns. But as I said before, there are several papers on these things for finding suitable movement patterns for almost any movement human possibly can do. Also walking stairs up and down. So basically, we just started with horizontal movement, but we can surely extend that a bit further.
About your ideas for is your kind of approach of using some good math and a few assumptions give you a good sense of the location of the device in space. Is there I'm just curious about your ideas about the accuracy of that. If you guys have any speculation on using other machine learning or artificial intelligence things to look at the patterns in this to maybe see, yeah, this is a ladder, this is a stair, this is a...
Yes, we have some plans for doing that, but basically we first want to focus on more visual approaches. So we are currently working on using a line detection within the video stream and map those lines directly with the 3D model in the background. So basically applying some kind of snapping algorithm. So in order to compensate inaccuracies within the detection of movement.